worked under the supervision of Professor Tim Romer, and okay, she has worked on various directions, various diverse directions in combinatorial commutative algebra, and now she's going to introduce Metroids, and definitely there are many other related topics which are of a research interest, which is particularly algebraic and geometrical aspects of Metroids. So Metroids are very rich structure, and I hope many graduate students haven't seen Metroid before, but please be patient and follow what Sarah is going to explain. She's a wonderful presenter. Over to you, Sarah.
Thank you very much, Imran. Hello, everybody, and welcome to the first session of mine. As Imran mentioned, I'm going to talk about Metroids and some related topics. In the first session, I try to give you a basic introduction to Metroids. And afterwards, we try to, in the next sessions, we try to see which other objects can be attached to these Metroids, like polytopes, algebras, and ideals. So we'll see where we can go. But let us start with an introduction to Metroids. I would like to start with an example. Consider this matrix that you see on my screen. You see this matrix A with 7 columns. And I would like to just take the set E to be the labels of the columns, namely 1, 2, 3, 2, 7. And I would like to consider this set I, which consists of some subsets of E. Which subsets? I take those which actually contains the columns which provide linearly independent vectors in over R. Okay, so in our example, this I would be then just those subsets of E minus 7, for sure, because 7 is just 0, such that because of the rank of this matrix, these subsets I should have a cardinality at most 3. And for example, since these two columns 5 and 6 are the same, this I should not contain 5 and 6. Okay, because I'm taking those columns which are linearly independent over R. And now I should also avoid to consider some 3 subsets, like maybe I cheat a little bit, that maybe just 3 of them. Actually 1, 2, 4, we can also check if I'm right. 2, 3, 5. And finally 2, 3, 6. Okay. These are the only subsets of E, the column labels, that the corresponding columns provide linearly independent vectors over R. Okay. And now I would like to tell you that this pair E and I, with this structure that I mentioned, is indeed an example of a Metroid. So let us keep in mind this example. Now we provided a Metroid. We don't know what a Metroid is exactly, but this structure gives us a Metroid, working with a matrix like this. But now I would like to ask you to look at this set I again and check if three properties that I'm going to mention are satisfied. So the first property, which I call it I1, is that this set is non-empty. It's clear. It is always non-empty. In particular, we know that empty set is always inside I. Can take no columns. And the second property is that this set I is closed under inclusion. Namely, if something is inside I, and I know that Y is a subset of this X, then I can deduce that Y is also an element of I. So it is closed under inclusion. Again, you know from linear algebra that this holds clearly, right? Because we are working with, in the above example, we are working with linear independent sets. And finally, the third property says that if you have two elements, elements of this I, and you know that the cardinality of one of them is less than the other one, then you can deduce that there is something inside the bigger one, but not in the smaller one, such that if we add this element to the smaller one, we get again an element of I. So this is not also difficult because you know this from linear algebra, that if you have two independent sets, one is bigger than the other one, you can add something from the bigger one to the other one and get again linear. By linear here, really, linear independent, we really mean what you know from linear algebra. So we can also check easily the third one, and I know, I think everybody knows this. So it is easy to see that these properties hold for our above example. Okay, but now I would like to ask you to consider these three properties more seriously, because now I want to give the definition of the Metroid, and these three properties play an important role for me. Okay, so a Metroid in general is indeed a pair like E and I. I'm using the same notation because I think it's useful. So a Metroid is a pair E and I consisting of a finite set E. So we do not need to start with columns of a matrix. We can start from any finite set E and a collection of subsets of E, namely this I, which satisfy properties I1 to I3. So if we start from any finite set like E, and then take a collection of subsets of E, with this condition that those subsets satisfy these three properties, then we call this pair a Metroid. And then this E is called the ground set. And the elements of I, just motivated by our example, are called independent sets of Metroid. So E is the ground set, and the elements of I are independent sets of our Metroid. And now the Metroid that I considered here, our example, which I claim that this is Metroid, and we check that, okay, this the independent sets satisfy these three properties. Now it's clear that it is really a Metroid. Now you can believe me, right? And this special type of Metroid that we saw in our example, so our example, not example, I mean our structure in the example, not the specific 7-column matrix, is called vector Metroid. But we considered R as the field. Depending on which field we take, the story can change a little bit, okay? So that's why we would like to name it more precisely. Such Metroids, depending what the field is, are also called F representable. And again, in particular, if you take F2 representable Metroids, I mean, if you take the field of just 2 elements, then they simply are named by binary Metroids. And binary Metroids are an important class of Metroids, and there are various types of classifications for them, and we also return to them. We talk about them a bit more, maybe in the next sessions. So I think now we know the definition, and we try to see another example. So another example. I take a finite set E of cardinality n, whatever it is, and I take an integer R between 0 and n. It can be anything. And to have a Metroid, I need a set of independent sets. So I put I to be those subsets of E which have a cardinality at most R. And then we see that this pair E and I is a Metroid. So it's not difficult to check this. Okay, our first property was that I should be non-empty. Okay, so for sure, at least I have empty set here in I. So this is non-empty. The second property was that it should be closed under inclusion. It is clear. I mean, if I take a subset J of some I which is inside this set, of course, this has also cardinality, it's most R, right? So J has to be inside I too. And the third property says that if I take 2 elements of I, such that one of them has more elements than the other one, it has more bigger cardinality, then I can add something from X to Y and get again an independent set. This is also trivial because, I mean, when I have something which has less than cardinality, to take, maybe I just write a little bit here. If I take X, which has cardinality at most R, and if I take some Y, which has less than cardinality less than X, I mean, that's clear that I still have a space in Y to add an element to get cardinality at most R, right? I think that's too easy to see. So then one can easily see that, maybe I remove this part. Really, this set I satisfy I1 to I3, and this was just a definition of a Metroid. If we satisfy I1 to I3, then we have a Metroid. And this easy Metroid has also a special name. This type is called uniform Metroid, and notation for them is U for uniform, R, N, R the integer which is fixed here, and N the cardinality of E. Okay, so now we know another important class of Metroids, uniform Metroids, and some of them are very important in some classifications of other classes of Metroids. So here I can give you an exercise for those who are interested and would like to work a little bit with these new concepts, if they are new for them. Show that U24, so your ground set has 4 elements, and you're taking independent sets to be those which have cardinality at most 2. Okay, not so complicated. Show that U24 is not binary. We saw what binary is before. It cannot represent it. It cannot represent it as a vector Metroid over F2. You can just play a little bit around with linear algebra, and you can achieve the result. Okay, so you can see this fact, which is important. Actually, this U24 is one excluded object to understand binary Metroids. So there's a nice classification for binary Metroids based on just excluding U24 from the Metroid. Okay, let's see some new words in the Metroid world. One is that, okay, we are working with independent sets and maximal ones are called bases. And we usually denote them by B of our Metroid M. And if there is no confusion, I just write B, maybe. And very naturally, if a set is not independent, we would like to call it dependent. So non-independent sets are called just dependent. And among dependent sets, we would like to give a name to those which are minimal. And with maximal and minimal here, I always mean with respect to inclusion. So minimal dependent sets are called circuits of Metroid. And the set of circuits, the set of minimal dependent sets are denoted by C of M. And if there is no confusion again, I may write C. So if we look at our example of uniform Metroids, for sure you can say what the set of circuits is. Because here, this is the set of independent sets. Those subsets which are not inside this set are dependent. And they are those which have cardinality at least R+1. So if we just seek for the minimal ones, we should take those which have exactly R+1 elements. Okay, so in our example, we can see that C of URN is just those subsets of E such that the cardinality is exactly R plus 1, right? Okay. So now we would like to look at these circuits again to just see some properties, some very natural properties of them. So now, again, I would like to give you 3 properties, and I call them C1 to C3. First of all, we said that empty set was an independent set. So for sure, this is not dependent, and this cannot be minimal dependent. So never the empty set belong to C, because it was independent. So very clear. The second property, since we are talking about minimal dependent sets, this means that no 2 elements of C are properly contained in each other. So no 2 elements of C are properly contained in each other. They are minimal. This is impossible. So again, a very clear fact. And C3, the third property, which needs a little bit work. It's easy, but it needs a little bit work to observe it. Here, if we take 2 distinct elements of C, 2 distinct circuits, and we take an element inside their intersection. And then if we take the union, but exclude E, then this is dependent, or equivalently, it contains a circuit. Any dependent set for sure contains a minimal one, which is called circuit. So, as I said, this is not difficult to see, but I don't want to prove it here, because with a hint, you can easily see it. So let me put it as another exercise for you to show that this third property holds for circuits of a Metroid. And you can use, of course, the definitions, whatever we said so far, together with special attention to I3, the third property of independent sets. So this is not difficult to see. Okay, these properties hold for circuits of a Metroid. And I would like to, maybe we just check something for this example. I mean, let us check C3 at least for the set of circuits. We don't prove it, but let us check it for the uniform Metroid. So if we have 2 distinct circuits, what does that mean? We can assume that this is an R+1 subset, and you can think of this rectangle as another R+1 subset. And since we are saying that these two subsets, I'm looking at R+1 subsets, because here in this example, we showed that these are the only circuits of uniform Metroid, okay? So, and now, since they are distinct, for sure, we have one element in the red one, which is not in blue one, and we have an element here, again, is not in the red one. And if we take something in the intersection, and if we just take it out, okay, still we have R elements here, and for sure at least one element there. So what we get from the union, but not the one element that we take in the intersection, here in this example, has at least R+1 element. So then this is for sure a dependent set, and it contains a circuit or a minimal dependent set. So at least we can observe that in our above example, C3 really holds, but you can also prove it in general, and it's not difficult. Okay, so we started from the definition of Metroid, and we know that if we have some knowledge about independent sets, then we know the Metroid. Okay. On the other hand, if we have some knowledge only about the circuits, minimal dependent sets, for sure we know again the Metroid, because when you know the minimal dependent sets, you know that everything which contains a minimal dependent set is dependent. And when you know all dependent sets, those which are not dependent are independent. So knowing I gives us the structure of the Metroid. This is by definition. But knowing circuits also gives us the Metroid. We know everything about our Metroid. So this is nice because we can have two different points of view, looking at a Metroid through the independent sets or minimal dependent sets or circuits. Now, okay, we saw some examples with this point of view, and now I would like to provide an example with the other point of view, with looking at circuits. So another example, maybe. Now I want to start from a graph. And we use maybe some easy facts about graph theory, but not complicated ones. So this is my graph. I don't want to look at vertices that much. The edges are important for me right now. So I just label it as 1, 2, 3, 4, 5. I should check my notes, because if I label it in other way, maybe we have challenges later. Okay, and now I would like to take E as 1, 2, 3, 4, 5, the labels of edges. I keep it here. And now I would like to draw your attention to the edge sets of cycles of this graph. So this graph has 3 cycles, 2 triangles and 1 square. Maybe graph is not square really, but you can, it's a 4 cycle anyway. So I put the edge sets in 1 set. So I don't write the sets. I just simply, just to save time, I write 1, 2, 3, okay, and 3, 4, 5, and 1, 2, 4, 5. So these are the only cycles of my graph. For sure, you can see this is 1. This is the other one. Right? And finally, this is the last one. if you could follow my pen. Okay. Now I want to check if this set C satisfies C1 to C3. Okay. What was C1? Maybe we take a look at here. C1 was that empty set should not be in C. I mean, of course, our C has 3 elements and none of them are empty set. So this is fine for our example. Let us see what C2 says. Because of the minimality, C2 says that no 2 elements of C are properly contained in each other. You see that 1, 2, 3, 3, 4, 5, and 1, 2, 4, 5. None of them is properly contained in the other one. So C2 is also fine in our example. And C3 that we checked it for uniform Metroids. Let us see if this is also true in our new example or not. If we take 2 distinct circuits and take an element inside the intersection, let's see what happens to the union except small e. For example, let me call this as C prime, for example, and here C double prime, okay? If I take C and C prime, which are for sure distinct, there is one element 3 inside their intersection. And if I look at C union C prime and exclude the 3, what happens? This is just 1, 2, 4, 5. 1, 2, 4, 5. This is exactly C double prime. Okay, in the third property, we needed to say that this contains a circuit. In this special case that we checked, it is indeed a circuit, right? Or for example, if I take C prime and C double prime, in the intersection, I can take 4 and also 5. Let's just try 4, for example. So then C prime union C double prime except 4 would be 1, 2, 3, 5. 1, 2, 3, 5. This is not a circuit like the previous case, but it contains a cycle. It contains C, right? 1, 2, 3, yeah, C. And you can check also the other case, but it seems that, yeah, the property C3 also holds. Okay, in this example, we took some E, and then we took a set of subsets of E, which satisfy these 3 properties. And we said that knowing circuits gives us the structure of the Metroid. So in this way, we are providing a Metroid starting from a graph, taking the ground sets to be the edge sets, and taking the circuits to be the edge sets of cycles. In this way, we are getting a Metroid by knowing the set of circuits, because we saw that it really satisfies these properties, which is called, for any graphic, we do this. Graphic Metroid. Again, another important class of Metroids. that people work with it very much, and it has several applications in other fields. So, and now that we know our Metroid, what do I mean? But we know our Metroid, I mean that we know all dependent sets, as you see, by knowing circuits, and also independent sets. And in particular, the bases were maximal independent sets. Okay, so how can I get them? So, I mean, when dependent sets correspond to cycles, independent sets, we know that they should not be dependent. So an independent set should not contain any cycle, right? So if I take an independent set, maybe I write it, independent set is not dependent. I mean, this is clear. It means that independent set does not contain any circuits, right? And we know what circuits are here. So I can list all independent sets. But just to save space and time, we can just look at bases. For example, if I look at the edges 1, 2, and 4, 1, 2, 4. For sure, this does not contain any cycle. And I cannot extend it to a bigger set with this property, because once I add 3, for sure, I will see 1, 2, 3, a cycle is contained. So I'm not allowed to add 3. And also, if I add 5 to this, again, I will get 1, 2, 4, 5, the bigger cycle. Again, not allowed. So this is a maximal independent set. This is not dependent because it does not contain any cycle. So it is independent. And since I cannot extend it to a bigger independent set, it is maximal independent set or a basis. In this way, we can list the basis of this Metroid. Maybe I just see here and so maybe I just give you the list here. You can check that all these sets do not contain any cycle, and they are maximal with this property. So it is really the basis. Okay, this means that we know now our graphic Metroid associated to this graph very well. And maybe the notation for this Metroid I should add here. If you start with the graph G, then this is denoted by MG. Okay, still we stay in this example. I would like to provide another set. Then I will tell you why. But for the moment, I would like to provide another set in this way. I take the complements of the bases above. So I take E, the ground set, minus B for any B inside the basis set. Okay, so this is an important formula for us. And in our example, what would be the case? So for example, for 1, 2, 4, I would get 3, 5. For the other one, I get 3, 4, and etc. Right? And again, if I just try to give you the complete list here. sorry. Yeah. Keep this set here for you. And now we have the complete list here. You can check if I am right. So I took the complement of each of the elements of B above in this set B star. But you can check that this B star together with E as a ground set provides a matroid, which we denoted by M star in general, if you start with any Metroid, and here I get MG star, which is called a co-graphic Metroid. You can check that this gives you a Metroid. This is not difficult at all, because knowing this B star, this set, as a basis, you should take all subsets of them. For example, you should put empty sets as well as all singletons, okay? Then you have the set of all independent sets. And then together with this ground set E, these independent sets gives you a Metroid. For checking this, you only need to check if I1 to I3 hold. It's very easy for a few sets of cardinality at most 2. It's more than clear, okay? And after knowing that this is a Metroid, we call this Metroid a co-graphic Metroid. And we don't need to be in the world of graphs and graphic Metroids. In general, if you have a Metroid with ground set E and basis B, you can always take this E as the ground set and provide this B star in general by taking the complements of elements of B. You would get a Metroid M star, which is called the dual Metroid of M. And this dual Metroid with the same ground set as M has its own independent sets, bases, minimal dependencies, namely circuits, dependencies, everything. And we can call them for M, namely the bases of M are called co-bases of, bases of M star are called co-bases of M. Circuits of M star are called co-circuits of M, and etc. Okay, so this dual Metroid also has nice properties. And one thing that you may expect to have when we talk about dual, you may expect that after taking 2 times dual, you get back whatever you had in the beginning, the original Metroid. And this is the case here, really. You can check that M star is exactly the same as M. You can work a little bit with definitions and you take back your M. It's clear almost because of the definition of B star, because you are taking twice complement. So you can easily check that this equality also holds. And as an example of a dual, we saw this co-graphic Metroid that we would like to look at it more precisely right now. So this was our graph. Let us go back to our example again. This was our graph, right? And the label was 1, 2, 3, 4, 5, just to have it in. I'm sorry. Okay, here we saw the basis of co-graphic Metroid. Knowing basis, we know all independent sets. Therefore, we know all dependent sets and circuits, right? So we can easily list the circuits of this Metroid. The circuits are those which are not inside this set B star, and they are not subsets of them, so we can easily list them. Again, I may try to give you the complete list. You can later check patiently if all are fine. Oh, sometimes it does not work at all. Once again. No. Okay. So. And as you see, I mean, at least I can tell you here you have some 2-element subsets of edges, but there are 2 subsets of cardinality too that you don't see them here. So for sure they are dependent sets, and they are 1, 2. You see, you don't see 1, 2 here, and also 4, 5. Again, you don't see 4, 5 here. So since they are not independent, they are dependent. Okay. And since they are minimal with these properties, because singletons are all in this example independent, so that's why you see 1, 2, and 4, 5 here. And similarly, you can get the whole list. But in the graphic Metroid, when we worked with cycles, we saw that, okay, circuits have meaning in terms of the graph. Circuits of the Metroid, graphic Metroid, were exactly the cycles of the graph. Let's see what circuits of the dual Metroid or co-circuits of the graphic Metroid mean in the shape of the graph. So let's look at this 1, 2. Okay, 1, 2. If I remove 1, 2 from the graph, what I obtain would be this triangle 3, 4, 5 together with this red point. This removal of 1, 2 from the graph separates this red point from the rest of the graph. Or if I take, maybe I draw one more time here, the graph, 1, 2, 3, 4, 5. And now I would like to look at this point and these 3 edges because of this 1, 3, 4. If I remove these 3 edges, what happens? This removal separates this blue point from the rest of the graph, 2, 5. You can check for all other ones. The same story occurs. So this set of edges whose removal from the graph increases the number of connected components of the graph in graph theory are called edge cuts or simply cuts here. So what we see also here is that these sets are all minimal with this property. If I remove just 1 and keep 2, there is no separation here. And also vice versa, if I remove 2 and keep 1, again, there is no separation. And here, if I keep one of these 3 edges, for example, 1, then there is no separation. We can see the same for 3 and 4. So what we see here is that this set C star, the co-circuits of the graphic Metroid, or the circuits of co-graphic Metroid correspond to minimal edge cuts of G. So we can read the circuits from the shape of the graph, both in graphic Metroids and co-graphic Metroids, which is nice because we can have more flexibility in working. We can have more intuition about what we are doing. So this is also the case. And for edge cuts, maybe I just write that if X is the definition for those who do not know about graph theory, the set a set X of edge sets E of G such that G minus X has more connected components than G. So just to close my talk, we may have a summary that what we saw in this talk, what we understood, hopefully, is that, okay, now we know what Metroids are, and we know some special classes like F-representable ones, in particular over F2 binary Metroids. When we started from a matrix. And when we started from a graph, we had graphic Metroids, another important class. As the dual, we saw co-graphic Metroids. Another class, an important class, are URN, uniform ones. And for any Metroid, we know now what are the concepts of independent sets, maximal ones, basis. This was I, this was B. Dependent sets for sure, and minimal ones, circuits, C. And also we saw that what are dual Metroids with the set of bases B star and circuits C star, co-bases and co-circuits. And maybe later in the next sessions, we see more about Metroids whenever we need something. But we will try to, for the next session, we try to associate a geometric object, namely polytope, to the Metroids that we are looking at. And we will see how far we can go. And now I think I can stop my talk for the first session here. And yeah, that's all. Thank you very much.
Thank you very much, Sarah. Any questions? Maybe we can go to the chat box first. Are there any, Numan? Okay, there is a question by Aksa. Sarah, can you read that? You discussed the minimal dependent set. My question is, what is the difference between the minimal dependent set and minimal dependent set as described?
Maybe I see the chat box somewhere. I don't see it right now, but.
Okay, the question is, what is the difference between what is the difference between the linearly dependent set and the dependent set you are using here, probably in the context of, yeah.
Okay, so, I mean, I started from an example from linear algebra, and there I really meant by linearly independent or dependent, no matter, I really meant what you know from a linear algebra course, okay, over some field. But this was just an example for me. Now we went further. We tried to define dependent and independent sets abstractly in terms of Metroids. So for me, now in the world of Metroids, an independent set is a subset of a finite set that I took, which satisfy these three properties, and a non-independent set, a set which does not satisfy these properties, or in other words, a set which satisfies these three properties is called dependent. And linearly dependent sets, what you know from linear algebra, also satisfy these three properties. So they are, when you start from a matrix in our first example, they are special cases. But we had a more general concept here. I hope
Maybe
I could answer.
Maybe you stress more on the minimality of the linearly dependent set.
Yeah.
Because the question. Yeah.
Oh yeah, minimal is just under inclusion. I mean, if I take something like in this example, let me go back to this example, uniform Metroids. Here, uniform Metroids, these sets are just the independent sets. Suppose I take N4 and R2, the one that I gave you as an exercise. Okay, so here the independent sets are, as you see in the definition, those subsets which have cardinality at most 2. Okay, so and if E is just 1, 2, 3, 4, then I have empty 1, 2, 3, 4. They are singletons. And then 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. These are all independent sets. Those subsets which are not here are dependent sets. Which one are not here? Dependent sets. Those which have cardinality at least 3. So 1, 2, 3, 1, 2, 4, 1, 3, 4, 2, 3, 4. And 1, 2, 3, 4. But if I'm interested in minimal ones, what I take are these 4 of cardinality 3, because this contains the other ones. So I just drop this from the set, and then I call this minimal dependent sets, which is C. So in my language now, this is an example of minimal dependent sets. Is it clear enough?
Yeah, thank you. I think now it would be clear. There is another question. Again, this is regarding to the dual of the circuit. And I think it is from IBA. The question is, can we drop 135 from the example you have mentioned? I think this is quite clear. Anyways, okay. Would you like to answer? Go to the example of the circuit dual.
Yes. Now, well, what was this set? Maybe now I can see the chat box. 1, 3, 5, right?
Yeah.
Okay. If we remove, let me draw the picture again. Here. This was the picture. 1. You should not make a mistake in the picture. The labels 1, 2, 3. Okay. 1, 2, 3, 4, 5. And if you remove 1, 3, 5, what you get is just 2 and 4. And as you see, again, there's a separation. This removal gives you a separation, gives you more connected components. And this 1, 3, 5 is also minimal with this property, because if you keep 1, then there is no separation, right? This is 1. If you keep 3, again, there is no separation. So here, and also if you keep 5, again, there is no separation. So this 1, 3, 5 is really a minimal edge cut, the same as what I told you in 2 special cases. So again, this has the same meaning as what we had for co-graphic Metroids. Great.
Now, there is a little bit long question that what is the relation between Metroid and simplicial complexes? Because B you described reminds the maximal faces and B steric reminds the minimal non-faces of simplicial complex.
Yeah, it's a very good question. And Metroids are indeed simplicial complexes. So because if you know what a simplicial complex is, you know that it is closed under inclusion, right? And in the second property of independent sets, we see this is all the same. We had the property that if there is some X inside I, then all subsets, maybe I'll show you again that property here. If you have something in I and a subset of X, then this subset also has to be inside I. So the set of independent sets of a Metroid provide a simplicial complex on the ground set. So there is a very close relationship. But Metroid has a more maybe complicated structure because there are more conditions on it. So there's I mean several studies on it because it has its own history, but they are simplicial complexes.
Yeah. Now, thank you. Any other question from the audience here? Hassan would like to ask.
Okay, Professor Sarah, thank you so much for such a nice lecture. I have a question about, you mentioned that if we have a Metroid, we can have a dual Metroid from that. So are there any methods in Metroid theory as well through which we can obtain a Metroid from the given one, which is not necessarily the dual?
Let me ask you if I understand your question well. You say that, okay, here I had a Metroid. Maybe I bring some space here. So I have a Metroid, and under some work, I got another Metroid M star, which is not always another because they can also be isomorphic. But anyhow, I got this M star. You mean that if there is another way that we obtain some other Metroids from M?
No. Yeah, I mean, the M star need not be dual. Such a Metroid which is not the dual one.
If you start with the structure that I mentioned, for sure you get the dual. I mean, if you really work with the complement of bases, for sure you get the dual. But I'm not sure if I understand your question well.
No, I mean, the question is, if we are given a Metroid, can we get another Metroid from the given one, which is not the dual one, some other Metroid?
I mean, sure, if you go another way, if you do some other construction, if you try some other procedure, for sure you can. For example, we have some operations on Metroids. We delete something from a Metroid and we get a new Metroid. We contract some elements from a Metroid and we get a new Metroid, and several other operations on the Metroid. And we will see some of them in the next lectures.
Yeah. Oh, any other questions from the audience? Yeah, Hibsa.
Can we define a Metroid? Can we define a Metroid?
Speak again.
Can we define the Metroid structure on a poset?
Sorry, can you repeat, Imran?
The question is, can we define the Metroid by using the poset property? I think she intends to give, we can use the poset lattice to introduce the Metroid.
I mean, Yeah, it's possible because I mean, there are several ways of looking at this question, because when you have a poset, you have also, you know, that you have graphs associated to your poset. I mean, beside the Hasse diagram, you have also comparability graph and incomparability graph. So in this way, yes. On the other hand, if you take the order complex of your poset or your lattice, again, since you have a simplicial complex, that simplicial complex, if you add some structure to obtain, for example, the third property of what we had, again, you can have a Metroid. And yeah, I can say yes.
Okay, Sarah. Now, are there any questions from the audience? Yeah, there is another.
Why it is important to find the basis? What information do we get from the number of elements in the basis?
What intuition we get?
Yeah, probably the question is linked with because everything is defined in the context of linear algebra. So basis, the count of the member on the basis defines the dimension. So probably the mean, he means that whether the count of bases means something here in Metroid theory.
Okay, so if I understand well the question, I mean, the number of bases, maybe not that much. I mean, what is the cardinality of the basis, but the the cardinality of the maximum, the biggest independent set, the biggest basis gives us the rank of the Metroid. I didn't define these concepts because we don't need them later, but yes, for sure, you can get the rank of the Metroid, which is important very much in several formulas in Metroid theory. So the biggest cardinality of bases, this is important, very important.
Is there any other question? Yes. Yeah, there is one.
Ma'am, at the start of the lecture, in the example of where we take matrix, we define Metroid by using the linear independence. But in the definition, we use the containment properties. My question is how these properties implies linear independence. Maybe if you can provide a hint so I can do it by myself.
Sarah, may I translate? Or do you understand?
I mean, I could not hear very well.
Okay.
I just understood that he's asking about.
Okay, the question he is asking, okay, you begin with the motivation of the Metroid theory through using the independence, and then you gave some example where, particularly your example of URN, where everything is with the containment. So his question is independence. How independence implies with the inclusion property in URN? Are they interlinked or they are independent structures?
In uniform Metroids,
yeah.
I mean, in all Metroids, of course, independent sets are in the second property in the definition are closed under inclusion, right? And then here I listed actually the independent sets for one of the audience. Here you see that I just provided all elements here which have cardinality at most R, and this is for sure closed under inclusion. Am I clear enough, or should I explain?
Yeah. Okay, and particularly the inclusion of the empty set. That is okay. Sarah, my question, now I have one question. So if we see the Metroid of the graph, so particularly they are the spanning tree. Spanning trees are the one which appears in the basis. So graphically, how can we see the member of the circuits in graph? In the basis, I think I should say a kind of.
Yeah. Let me, where is my example of graph? Yeah, here, right? So
Yeah.
here, the cycles of the graph are circuits of my Metroid, the cycles, really cycles. And yeah, and as you said, I didn't mention this, but you are completely right that I just talked about independent sets which should not contain any cycle, but if you want to look at the maximal ones, they correspond to spanning trees if you start with a connected graph, and a spanning forest if you start with a disconnected one, and yeah, which is a good comment. But the
okay. If we modify this graph and you can whisker any edge maybe on anywhere, so will it change the circuit, or circuit will remain the same if we whisker this graph?
If you add something, by a whisker you mean adding a whisker to
edges,
any
another edges.
vertex?
Yeah. Will it change anything in the circuit? No.
In the circuit set, no. Okay. Because it does not influence on the cycles, for sure not.
Yeah. Okay. We are done with the question answering session, or are there some other questions? So seemingly there are no questions. Thank you very much, Sarah, for very nice talk. Please give her an applause.
Thank you for your attention, and see you tomorrow for the next session.
Okay. Take care. Bye-bye.
Thank you, and bye, everybody.